what we are covering, we looked at in general airborne networks. It is how we can support, how we can provide communication support for drones. That's one aspect. In the very first lecture, we focused more on the how can we use drones to support communication on the ground by discussing airborne networking. You need to provide communication to for the drones. So, and we have looked at three scenarios. One is you can have a radio on each air vehicle. That way you can create something like a mesh networking or ad hoc networking. And we also talked about near impossibility of creating an ad hoc network in the airspace. It is nearly impossible because of the dynamics. If you think about tens of drones and you want to establish a network of drones, then because the vehicles are moving so fast, it is difficult to maintain the network. Even you somehow create a network, it's going to break. Links are going to break very quickly, right? So even though we have the idea of mesh networking, like a mobile ad hoc network, these are common on the ground, but when it comes to airspace, it's not easy. Okay, then we also considered there are other options like cellular network supported airborne networking, or of course you can use satellite also. So each of them have their own pros and cons, and specifically there is a lot of emphasis, a lot of push from the cellular service providers to come up with a framework using the cellular network or cellular service for providing communication for the drones. So 3GPP, especially new releases starting from 17, 18, 19, all these are primarily focusing on non-terrestrial networking, and that includes communication support or cellular communication supported airborne networking, right? So one thing is, irrespective of whether you use mesh networking or mesh radios or cellular service or satellite service, the discussion that we started yesterday is about drone-to-drone communications. Irrespective of the radios, irrespective of the networking support, we need to have some sort of a protocols. So that is what we are discussing. Drone-to-drone communication protocols is the center theme that we have been discussing. And today, even though on the schedule we have swarm networks, we will move that to some other day. But today I will continue discussing drone-to-drone communications. Again, my goal is to make sure that those who are working in this field or who are thinking of working in this field have something to take away from this lecture. So it is better to go in detail. At the same time, we are not discussing lots of equations and mathematical models because you can always find them on the papers. I wanted to give you the big picture first, and we'll take one problem and go deeper, just one problem. Okay. So today's talk is, So today's talk is more on continuation of what we started yesterday, and we just briefly review what we learned yesterday, and then go more get into more details. And in the afternoon, in the second lecture, I will actually look at one particular problem, a research problem, in more detail, so that if at all you are looking for a problem in this area, research problem in this area, you could pick it up. All right. So in terms of drone-to-drone communications, we looked at three perspectives, three aspects. One is what are the use cases, and then how use cases can be implemented. So some sort of a algorithmic approach. What kind of process or algorithm will help us to implement the use case. So that's two. So use cases and implementation. Second. Third is a model where a tunable model to create a airborne network including drone-to-drone communication, or more specifically drone-to-drone communication. If you want to establish a drone-to-drone communication link, then we'll discuss a tunable model that you can adjust according to the requirements. This particular problem is actually suggested by one of the NASA program managers, because so far in some of the research or real world applications. So for example, there was a remote ID concept we talked about. So remote ID is a broadcast message that goes from one drone to nearby drones. So typically, the purpose of the remote ID is to increase the situational awareness. For example, if every drone is sending a message, broadcasting a message, every other drone will know that, okay, there is this drone present in the vicinity. So same thing happens. So if you focus on one particular vehicle, then if it receives broadcast messages from every other drone nearby, then it has an idea of the situation around it. So how many drones are present, where are they heading? So you can have something like a model within the one drone, so that it can maneuver, it can navigate, avoiding any potential conflicts. So look at this carefully. Let me repeat. A simple broadcast message from every drone in the airspace will allow every drone to have an idea about which vehicles are nearby and how far they are and which direction they are heading. So that will allow the drone to navigate safely. But of course, you need to implement some algorithms and all that, but at least you have an idea. For example, let's say when you are driving, if you look around through all your mirrors, normally we do that all the time. When you look around through the mirror in front of you and the two mirrors on the sides, you have an idea about which vehicles are nearby. In fact, in the beginning, when I was learning driving, I was asking one of my friends, how do you make sure that you are, when you turn, when you change the lane, there is no vehicle next to you? He said, in your mind, you always have an idea about which vehicle is next to you, because you look through the mirrors once and you have an idea about what vehicles are there, and once the vehicle passes, you know that, okay, the vehicle passed, there is the next vehicle. So you always have to have that situational awareness. So that is possible with remote ID, or in the commercial aviation, you can think of ADSB. Now, we talked about ADSB. ADSB is for commercial aviation, commercial vehicles, and remote ID is for the drones. So all we are doing is simply sending a broadcast message. Every vehicle sends a broadcast message. That is good enough to have a situational awareness. However, it is not sufficient for avoiding conflicts. Especially when the vehicles are so close, you need to have a two-way communication. So remember, ADSB also provides a means to communicate. You can always send a message. You can also get a message. But what we are looking at is, when you say drone-to-drone communication, a standard communication protocol that will allow us to negotiate right of way and merging into the lane. So those are possible with V2V communications. The intention is to develop a standard, but that is probably it's a long way. Definitely the industry needs it, and then when the advanced air mobility services scale up, that means today we don't have air taxis, unmanned air taxis. Of course, you have air taxis with the helicopters and all that. If you want a ride, yeah, you can go for a ride, but it's not like a subway system. It's not like a regular a fleet of vehicles in a city. So that will happen sometime down the lane, but even you have tens of vehicles, it makes sense to have safety mechanisms. In this case, collision avoidance is certainly a very important aspect of traffic management, and that is what we are trying to do. All these are new areas, and which means that there is a lot of contribute, because the subject is rich and the topic is new, and it will allow you to contribute, to make your own contributions. Okay, for example, I was talking about the idea of air cells, and it's it's a topic, it's an idea that started in my lab, and we presented a lot of papers, and I filed patent, my students are filing patents and all that. So same way, if you pick some topic within that is connected and you think deeper, then you will be able to make some contributions. Okay? For example, the highways in the sky, this is just an idea. Nothing has been done. There are no standards. It's still evolving. So keep that in mind. It's a very rich topic that you will be, if you take up as your master's thesis or PhD thesis, there's a highly likely that you can make some innovative contributions. All right. So what are the use cases we talked about? Collision avoidance, information relay, collaborative sensing, minimum separation distance or maintaining minimum distance of separation, and airborne rerouting. These are the 5 use cases. Remember where they came from? They came from the industry. A working group called RTCA, Radio Telecommunication Association, or for avionics, I believe. So they meet quite often. In one of the meetings, in one of the recent meetings, they said, okay, what are the main applications, main use cases we want to address? And these are the use cases that came from. So what I did, I'm a chair of IEEE 1920.2, which will be released to public very soon by end of the year potentially. We are in the final phase. So in that group, we started with the use cases and investigated these use cases in more detail and came up with a set of messages and the protocol for implementing all these use cases. So once again, you remember in the discussion yesterday, I said the right way to begin to develop any standard is to start with the use cases. And obviously, you cannot enumerate all the use cases in the beginning. You may not know what use cases come up in future. Okay? So in that context, it's interesting to see things like Facebook and YouTube. We never imagined that they become so successful. They are successful because there were so many applications and use cases that came up that you never thought about. For example, I thought when Facebook came, what is the big deal having your photo? What's the big deal? But today there are so many things. You can Facebook groups are there, especially YouTube. Today morning I was watching when Dr. Sai Prakash visited me in the room. I was watching Schrodinger's wave equation on YouTube. Can you imagine that you learn like physics and even whatever lectures you see? This could be maybe put on the YouTube. That way anybody can see anytime. So sometimes you may not predict what use cases are going to come up. Okay. So the point is we have 5 use cases that are coming from the users. So we dive deeply into these use cases and came up with a set of messages, okay, and protocol. So the question is now is it enough? Now we are releasing the standard probably by end of the year, but it may be enough or may not be enough. So one thing that I am planning to do is I will open up a competition for students and then say, come up with a use case, any use case other than this, and see whether you can use the standard that we develop and tell us whether you are able to completely implement the use case based on this, or you see any need for more messages or different kinds of messages. Okay. So I'm going to talk about what's the specific messages very soon. So the point is, that is how we evolve, that is how we develop standard. The standard is not set in stone. Now for example, 82.11, so today you can see a series of protocols, A, B, C, D, E, right? So things evolve. And the second important thing is we are not focusing on which radio you are using, which frequency you are using. So in fact, to develop a standard, you also need to know what is the frequency band you are using. However, in this standard, in this IEEE 1920.2, which is for drone-to-drone communication, we have put that aside. We are not concerned about which radio you are using. So basically, it's a radio agnostic. So what does it mean? What does it mean by radio? So tomorrow, suppose the Federal Aviation or Aviation Authority in respective countries, they decide which frequency band to use, then irrespective of what frequency band, this protocol should work, because it's only a message. We are only defining messages. We are only defining the message format. We are only defining the fields within the message. We are only defining the protocol, or how you exchange information from a drone to drone. So given that, it should be applicable for whatever radio you are using, and maybe another standard might come up that will focus on which frequency band to use and all that. Okay, so it is applicable. It's not going to. This is not going to change. So anyway, so with respect to use cases, we spend some time. Yeah. So with respect to collision avoidance, these are the three things we talked about. In fact, yeah, collision avoidance means two vehicles are coming closer. So if we look at what are the scenarios when two vehicles may be coming closer, these are the three scenarios. One is something called crossroads, and we in this example or in this scenario, we are looking at a situation where there is no structure in the airspace, something like in rural areas where two vehicles are flying freely, and they are sharing the messages. And what type of messages? Broadcast messages. To begin with, you are only receiving broadcast messages, and as I told you before, that is enough to have a situational awareness. Basically you know which vehicle is nearby. But if you see that these vehicles are coming closer, and if based on the information that you have about the other vehicle, if you predict there is potentially maybe a collision, then we want to figure out how to avoid. And how do you do that? Once you know the direction of each vehicle, by the way, both vehicles have the same information. Now, your information is vehicle A's information is going to vehicle B, vehicle B's information is going to vehicle A. So basically they have the same information. There is a little bit one catch, we will talk about that in a minute. So having same information, they can predict exactly which location they may be they are heading to, and the choice is now the action. In terms of action, you have to avoid that collision. To avoid the collision, what you need to do? You need to have a predefined protocol. You need to predefine, otherwise it's not possible. You don't want to negotiate in the air. You don't have so much of time. So that is one more criteria. You want to have you need to come up with a implementation mechanism or negotiation process that can be implemented in few rounds, minimum number of rounds. So that is possible only if you predefine the protocol. So as I said, the protocol could be, once they identify they are coming to the same location, potentially there is a collision, then you need to define the process. Maybe for example, one of the vehicles will go up, second vehicle may be going down, and the first vehicle again goes up and left, second vehicle may go down and right. So that way you are creating a huge gap. So again, this is something that is this one option, but we are not predefining all those. Basically, we are leaving at a point where two vehicles are coming closer and there is an action item that has to be taken by both vehicles. So this is one scenario. The second situation is a structured airspace, something like this. When I say structured, you are defining the structure, you are creating cells. We call this as an air cell, and then air cells concatenated together form a lane, and multiple lanes form a highway system. So this is something like highways on the ground, or analogous to similar to highways in the ground. You can create highways in the sky. Now, if you Google and put highways in the sky, you will see lots of articles. Potentially you will see one of my articles too. So all this is, again, at this point it's all academic research. Okay, there is no real world implementation of this. And for each of these topics, by the way, there is a paper from my lab. My students have published papers, and some of them are conference papers and some of them are journal papers. So all this was actually possible because of advanced air mobility project that fortunately I was able to get in, and I was able to include my students to participate. And we are not only in fact, before we started thinking about these problems, the real motivation is the real world implementation. So this is something different. It's not that something started in the lab and we implementing in the real world. It's the other way. We saw the real world what you call projects. We were involved in the real world projects, and we saw the potential for doing this research. So research, in this case, research is coming from the real world scenarios, real world needs. That's an interesting aspect. Okay, but then into the research is topics are pretty, they require a lot of investigation. For example, I mentioned about channel models. See, the thing is, there was no reason for us to even study a channel model between two aircraft at the height of, for example, 4,000 feet. There was no need, because there were no planes. There is no need for creating a network in the airspace. And you might be thinking about commercial aircraft. Commercial aircraft fly at 30,000 feet. And even though the idea of ad hoc networking of aircraft has been there for long, it was in the military context. So when there is no need, who will do research and who will fund, right? So here the thing is what you call need-based research. We saw the need, and then now we are looking at channel models. Now we'll talk about that in the next one of the lectures. All right. So merging scenario is a scenario where one vehicle from one lane is trying to merge into the other lane, and it's not only for changing the lanes, it's also for a vehicle that is taking off, just using this. So one vehicle is on the ground somewhere, or maybe on the rooftop. It is trying to take off, and then it needs to merge into one of these lanes. So merging is required while entering the highway system, or when you change the lane. The third scenario is, we call it roundabout. Basically, it's like a circular intersection. Again, we'll see this in more detail. So there also a vehicle has to enter a circle and leave a circle. So we focus on how a vehicle enters the intersection. So that's where merging happens. That's where you need to avoid collision. So collision avoidance, understanding the collision avoidance, we looked at 3 scenarios, and for each of them, as I said, we have a paper published. I will share with you later. The other use cases, I'm kind of repeating what I did yesterday, but it helps you to recollect, and then understand the significance of the lecture or content here. So minimum separation is actually pretty easy, because once you know the location of the vehicle in front. By the way, before we get into minimum separation, we are imagining a scenario where a lot of vehicles are flying in the same lane. It's almost like a highway system. There is one after the other, the vehicles are flying. Like a subway system. You have 10 o'clock there is one train, 10:15 there is another train. Especially go to airport, you'll see the vehicles keep going. So there, the idea here is, as soon as you are listening, you are supposed to listen to the messages anyway. The information coming through remote ID or ADSB. So what information are you getting? You know the location of the vehicle in front of you. So the vehicle behind knows exactly where the vehicle in front of is located. And suppose the vehicle in front is slowing down, you're supposed to slow down. So that's actually natural. You don't need any protocol for that. So even though we picked 5 use cases, one of the use case, in this case, the minimum separation doesn't require any. We realize that it doesn't require any protocol implementation. But whereas the other 4, collision avoidance requires a negotiation between the vehicles. Merging requires a protocol, implementation of some sort of an algorithm or a protocol between 2 vehicles. Same thing with collaborative sensing and rerouting. Okay. All right, we discussed this before, but let me do a quick summary. Information relay refers to the information going from vehicle A to vehicle C through B. So B acts like just a relay. It doesn't do anything other than taking the information coming from A and passing it. That's information relay. And it is required because it's something like a multi-hop routing, for example, or multi-hop information relay through multi-hop. Another example is, suppose a ground control station. I need to give a little more details about what do you mean by ground control station. Suppose the ground control station, which is on the ground, is trying to send a message to every vehicle in the airspace. Let's say something major, something happened, every vehicle has to come down. These things happened, right? When 9/11 happened, we wanted every vehicle to land. And there are a couple of other situations we had that kind of incident. So what happens? The from ground control, you're sending a message to one vehicle or to nearby vehicles. All nearby vehicles get the message, and each of those vehicles in turn have to pass it on to the rest of the vehicles. So that is clearly an example, a use case for information relay. The collaborative sensing is a scenario where a major event or something happened, some event occurred in the airspace, but each drone or each vehicle can only sense to some aspect of some extent of the development, sudden development. Suppose there is a bad weather, it's raining. So one sensor cannot look at the whole picture, and it's not possible for one vehicle to look at the extent of the sudden development or bad weather. So then what happens? Every drone is supposed to measure. And what are we measuring? All we need to know is what is the area, what is the volume, to be specific, that you need to avoid. If it is raining in somewhere, then each vehicle will look at sense to the extent of the bad weather or raining area or volume, and then it shares that information to the ground. And at the ground control station, you can put all the information together and predict the overall extent of the bad weather. So that in that context, that is the spirit. Potentially what could happen is, when you dig deeper, when you go deeper into a specific use case, or you look at a variation of the use case, you may find some more information that you need to, or more challenges. But for now, since we are at the beginning, there is no work done in this area. So given that there will be first draft of this protocol, and then in future there will be more development. So collaborative sensing basically will help to understand the scenario or the context or the hazard we call airspace hazard, to estimate the airspace hazard fully through collaboration. Then the last item is rerouting. Now, rerouting is a scenario where, because of some weather or some other development, it's possible that there is a small depiction here, you can see. Yeah, there is probably a better figure later. But suppose you see bad weather somewhere, then we need to avoid the location. So potentially there are two scenarios. One is the vehicle itself can come up with a new route, but if it is not aware of the full extent of the hazard, then ground control station may have to send the new route. So if it is coming from the ground control station, then the vehicle that is directly within the range of the ground control station will get the message, but this vehicle may have to pass the information to the rest of the vehicles. So basically rerouting is a situation where, because of some sudden changes in the airspace or sudden developments in the airspace, we have to change the route in the middle of the flight. So to enable that, to make that happen, we need to share the information, just like similar to information relay. We may have to, for the immediate vehicles, for the nearby vehicles, you can send the new route. But if the vehicles are far away, then you have to combine this rerouting and information relay together to actually share the message. Anyway, so these are the use cases we discussed before, but now we get into some finer details. So this scenario we discussed before briefly, but again I'll provide the context, and we don't go into too much into detail. The key idea here is, look at this: two vehicles are somewhere in the airspace, and they are flying freely. There are no air corridors or any structure in the airspace. The process here is each vehicle has to predict if the vehicles are, if there is a possible or potential collision, and then the goal is to avoid the collision. So first thing is prediction. So look at some of the circles. Probably I didn't explain before. The circles are refer to sensing range and communication range. Okay, there are some other important elements here are even though you know the current location, suppose let's say this vehicle A and this vehicle B. Vehicle A shared the information to B and B shared with A. So the information is already present. Now what kind of information you have? You have the location, current location, then the direction, the speed. So given that, you can make a prediction. Now at what point, first of all, if there is a chance of collision, and what point, and then what are you supposed to avoid? How so this information is known. But it doesn't mean that you know exactly. This is only given the information at that time. Let's say you at T0 you have shared the information. So based on the information you have at that time, you are predicting that there may be a potential collision. But you don't know exactly the intent of this vehicle. Maybe after this at T1, maybe T0 plus 1 second, it may change the route, change the direction on its own. You don't know the entire path. So see the point. You know the intent of the heading of the plane, but you don't know exactly what's the next move. But typically vehicles don't change the direction randomly. So given that, based on the information you have, you make a prediction, and then the next step is you come up with as I said before, predefined protocol to avoid the collision. So this I think this is enough for now. Then we talked about the message. First of all, message structure. What type of messages are we going to share? So far we were able to come up with this kind of message structure. So one message is called discovery message. So again, since we are in the beginning, we can come up with names. So some of my students call heartbeat, and some students call it discovery message. Okay. So, but on the paper, once we finalize the draft, once we finalize the standard, there will be only one name. But you can call like heartbeat or discovery. No, these are the names we use. So what do you mean by discovery? It's just similar to remote ID. So in fact, I included remote ID here. And so remote ID consists of this information. So look at this piece. This piece of information has to be added as it is, because it's already a standard. We cannot change the existing standard. So given that, we use remote ID as it is, and then added all these additional fields. So this field contains, in fact, several sub fields: ID, drone ID, location and altitude, velocity, base station means ground control station, elevation, timestamp, and emergency status. This is the basic information. So think of like every phone will send a beacon, and that is how cell tower knows you are here. So for example, when I moved from Hyderabad to Warangal, how does the base station know that I'm here? Because every second or frequently, periodically, my phone is sending a beacon message, so the cell tower knows I'm here. Same way, every drone is supposed to send this as a broadcast message, like a beacon. As simple as that. So, but it contains the minimum information. There is a drone ID. Drone ID is something like a license plate, vehicle ID. In fact, it also contains IP address. So in the yesterday we talked about you are basically sharing the IP address. So is it safe? That we have to. Of course, it's not so safe because spoofing is so much possible. So one topic that immediately should come to your mind is security. Security has been studied a lot, but there is a lot more to be done. But anyway, we are not talking about security here. The drone ID is available. It also includes IP address, location, all this basic information is available. Timestamp, elevation, emergency status, all this basic. So we are not touching that. So when we were told that if there is a standard that is existing, you cannot override it, you cannot change it. You either use it completely as it is or don't use it. Okay? But the point is, this is not enough. We realize that this is not enough for us to establish a drone-to-drone communication protocol. So with that, we added several fields: vehicle name, vehicle ID, priority. We talked about this a lot. We talked about priority, telemetry. Telemetry again has some information that is common to remote ID. Role is, suppose there are some sort of formation mechanisms, or in a military context, or even in a search and rescue operations also, it is possible that one drone may be a leader, other may be followers. So basically you can implement leader-follower model. Then in terms of priority, for now there are only 3 or 4, high, medium and low, or no priority. But typically you are basically looking at, if a vehicle is emergency vehicle, then the priority is high. So these are the fields that we developed. Yeah, we'll move on to this. For now, this is enough to enough information to see. So basically, you have an idea, no? What type of information we are including, and how does it help a given use case. So the key thing here is, whenever you are defining a standard, you need to think about, you need to have minimum information. You should not be having redundant information. You should have minimum information, but sufficient. Minimum and sufficient information. Now, of course, if you think for some reason, oh, this is not enough, you can always add. So, but to some extent, you have to think into future and define the field lengths in such a way. So for example, priority is only 1, 2, 3, or 4. That means you're not putting only 2 bits over there. You're putting entire byte. So that way, in future, suppose for some reason you need to come up with 100 priorities levels, you can do that. So then normally a standardization process requires us to think ahead into future. At the same time, you don't have to define everything. Whatever information we know, whatever use cases we can think of, we fulfill them, but you can always extend. You can always extend down the line. Okay. Anyway, with that background, we learned about use cases, the 5 use cases. We learned about message structure. This is a typical structure for discovery message. And we'll talk about this called ROW, or right of way message. It is important for collision avoidance. We'll discuss that in a minute. Oh. Yes. Yeah. In fact, there also the real algorithm actually is based on the typically one drone will request for right of way. So one drone will request for right of way. The drone which has high priority typically requests for right of way. Then the solution is, the other vehicle will if it accepts, it will send an acknowledgement saying response for right of way, request for right of way, and response for right of way. So request is given by high priority vehicle typically, and the response is given by the other vehicle, provided it accepts. So once you get the response, then only you can assume that other vehicle actually got your message and is honoring the message. And then the vehicle that is responding will change the altitude or will reduce the speed. So that is the simplest protocol. Okay. So once again, remember, the protocol has to be predefined. If you don't define, it will be too complicated. You don't want to run so many. You don't want to send so many messages. The number of rounds of communication or negotiation has to be minimal. So given that, we are saying just only one request and one response. That's done. So for collision avoidance, that itself, that's enough. Now, unless obviously we have to test. When you come up with a standard, through simulations and through some testing, we think, oh, this is good enough, but we have to test it down the lane. And remember, as I was mentioning, These are all new area. This is a totally new area, and we haven't done a lot of testing. Even though we did something with the partner in partnership with a company, literally we flew the drones and we tested. Okay, but it's not enough. It's not enough unless we do a lot of testing, many tests, more experiments. We cannot conclude that okay, it always works. But keeping simple is the first rule. So and to do that, we should predefine the protocols, predefine some of the processes. So in this case, all we are doing is requesting for right of way, and you are getting the response for right of way. And of course, you still have to make sure the other vehicle actually did it, because what if something happens between after the request was honored, but then something happened. So you have to make sure that the vehicle actually is slowing down or change the altitude, then only you can continue. So those steps are still need to be followed. Okay, let's talk about merging. This we talked about this before. Merging is a scenario where a vehicle, let's assume that the vehicle that is in the pink lane or color box is actually going towards north, and it wants to move towards west. So this is north, south, west, and east. So this vehicle is originally flying towards north, and it's northbound, and is trying to move towards west. So that's, if you extend to other directions, you can. I think this is a typical diagram, and all these are called conflict points. So what it means is that if this northbound vehicle is trying to turn left and go towards direction of west, it's possible that there may be other vehicles here. So how do you handle that, right? And the solution that was designed or suggested by one of my undergrad students is very fascinating. In fact, again, what is the goal? You have to minimize the number of messages. It's not like you have infinite amount of time. You want to do it like a very effectively or efficiently using minimum number of messages. So how do you do that? Let me get to that in a minute. Yeah, here I think. Yeah. It is probably a little challenging to see this, but I will read it carefully. The first step is, this is a general merging process. Okay, so follow this. Basically, you are trying to change the lane, and potentially there may be other vehicles on this. It's a common sense solution really, but it was fantastic solution. You will see how it is so efficient. So first thing is listen to heartbeats. So what do you mean? What is a heartbeat? It's like a discovery message we saw before. So you know that there are vehicles nearby. So when the vehicle is trying to, for example, from ground it's taking off and it has to enter the lane, it's possible that there are vehicles in the lane. So you need to. How do you know there are vehicles? Because you have this heartbeat. You are listening to the remote ID or what I call discovery message or heartbeat message. So that means you know that where are the vehicles. Suppose there are vehicles here. Well, let's take the simplest case. If there are no vehicles, you don't have to worry about it. You just go. But so that is the purpose of listening to heartbeats. So it's almost like visually you are checking, are there vehicles before you merge, and instead of what you call seeing, you are actually listening to the messages, and if the vehicles are there, you will know and then you need to do something else. So the first question is, are there drones in the through lane? Through lane means in the main line that you are trying to merge. So that's the question we need to implement. No, then it's fine. You just merge, nothing. You don't need to do anything. But if there are vehicles, then you are checking for, do you have enough distance, enough gap, enough space to merge? That is this question. So that means there is a conflict. If there is a conflict, then you need to, so I'll skip some of these things. If there is conflict, then you need to implement, basically your understanding, there is a traffic. If there is traffic, you have to implement something called execute yielding process. That means you need to start an algorithm, a process. So basically you are checking the traffic, if the traffic is free, that means there are no vehicles, you don't need to do anything. But if there are vehicles, you need to begin a process. So what process is that? Yeah, we'll look at some detail. Okay. Yeah. So look at this. I think what this is demonstrating is. So what is the case one? Nothing is here. So you don't have to do anything. There is you're changing the lane. Okay. So this is, by the way, the one is in one direction, is this in another direction. So for example, from the previous figure, you're moving from northbound lane to westbound lane. And this is fairly easy, right? You don't need to do anything. But what about the scenario? Yeah, look at this. I'll just run it a few times, then you will see the idea here. Okay. So let's understand this. Okay. So this is the vehicle that is trying to merge, and it identifies there are vehicles in the lane, so it cannot directly go into this lane, and then it has to request these vehicles, one of the vehicles, to give the gap. Okay. So imagine in the worst case scenario, there are vehicles continuously, even though we are putting one gap. Maybe the scenario that I am presenting here is that that there is at least one cell gap. So minimum safety distance. Remember we talked about safety distance. So the point here is you are maintaining one cell as a gap, just for the minimum distance. So this vehicle is trying to get in. So let me, yeah. Okay. To be able to go like this, it has to start the negotiation process. So it is going to ask one of the vehicles to give a gap. So which vehicle it should ask? There is one vehicle here, one vehicle here, one vehicle. So it has to identify which vehicle is the right one that it has to negotiate. So that's a little small, there's some process is involved there. So instead of, so one idea is that this vehicle is already ahead, so you don't need to worry about this vehicle. And what about this vehicle? It remains that one of these vehicles it has to talk to. So let's check again. Yeah. So one way to think about it, it has to some sort of do some estimation, saying that okay, this is the potential vehicle that may be. It has to identify the vehicle that it potentially has a collision or a conflict. So you don't have to worry about this vehicle, but in this scenario, this has to talk to this vehicle to give enough gap. So all this is, it seems like complicated, but if you think carefully, because you know the locations and you have to define some sort of a circle, you have to define, let me go back for a second and see. It has to define, okay, which is the vehicle that it has to communicate. So in this context, it's very clearly, if it is going to merge here, this vehicle is too close. So it doesn't make sense to ask this vehicle to hold on or stop or reduce the speed. It's not going to work. So it is going to ask this vehicle to slow down. So follow this carefully. From among the vehicles that it finds potentially in conflict, it has to identify the vehicle which has sufficient gap already, and which is in a position to provide a gap or give a gap, and then negotiate with the vehicle. So that is, I believe, this idea came from just undergrad student, one of the undergrad student. So basically, to do research, you don't have to, of course, for an undergrad student, the knowledge is limited. For example, I teach communications course. For undergrad students, I teach only simple modulation techniques, like basics of AM amplitude modulation and frequency modulation, phase modulation, but they don't know the advanced techniques like MIMO and all those things. They don't know, but it doesn't mean that they cannot do research. In fact, sometimes what happens is they can do before taking the course, they can do the basic studies, learn the basics of the advanced courses, and then start working on it. And then when the time comes, when you take the advanced course, then you will be able to fill in the gaps. So to do this kind of negotiation, to do this kind of research, you don't really need to know advanced communications. For now, it is just a simple common sense logic that allowed us to allowed the student to figure out how to make this work. And another aspect is maybe this is not coming from books, just basically thinking about the problem, spending some time, and that might lead to a solution that you are looking for. So basically, a problem was given to the student, and the student spent some time thinking about it and came up with a solution, shared with me, shared with the, and typically ask the student has an opportunity to present with the group, because obviously we have research groups. So you present your idea to the research group, and that's how you get some feedback. And suppose you might have forgotten a certain aspect, you will know that, and that's it. That will lead you to, at least this is still research. This is a published paper, so that means there is some innovation and creativity involved in this. But later, when the student actually takes a master's level or get into PhD program, they can do even more. But the point is, you need to think through the problem, spend some time on the problem, and come up with a solution and discuss with your peers. That's what is required. So this algorithm it meets the requirements. As I said, we want to design a solution that requires minimum interaction, minimum set of messages, but yet you have to get the job done. And does it work all the time? Probably it won't. But in scenario that we described, we are assuming that all these vehicles are cooperative vehicles. So for that scenario, it works. In fact, typically, any vehicle that even flying in this corridor must have the requirement, or meet the requirements. There is a idea of requirements for advanced air mobility vehicles, which means that yes, it will be certified to fly only if it meets the minimum requirements. And what are the minimum requirements? It has to have the radio. It has to have should be able to communicate for certain range, within certain up to certain range. So all these have to be met. So the point here is, all these vehicles are expected to meet the minimum requirements. Then only they will be allowed to fly. You won't be able to fly small drones into this area. So remember, these altitudes are about 4,000 feet. It's not set in stone, but about 4,000 feet. That means about 120 meters or so. So we're not talking about small drones. Small drones may not have the ability to have V2V communication. Okay. So with that in mind, the solution here is very elegant, very simple, and it is effective. Okay. But we have to see, it doesn't mean that's the end of the story, but over the time will tell us whether we need to have any modifications. So that's the idea. So in this case, we need to think about the concept of gap. How much gap basically you're asking, this vehicle is asking, create a gap for me. So that means in this, look at the circles. The circles are giving an idea about how to choose the vehicle that you want to communicate. So for example, when you are trying to merge, this vehicle is already gone. So this is the vehicle that you need to talk. And any other vehicles, probably if there is a vehicle here, there's not enough time for it to give you the gap that you are looking for. So you have to identify the correct vehicle, right vehicle that is in a position to give you the gap that is necessary, and then this is the amount of gap that you are looking for. So this picture depicts, and finally these are the quick steps. Identifies the topic, search for the right candidate, right drone, sends the request for gap, awaits the gap formation, and then merge. So this is what I meant by simple, sufficient, and will do the job. Yeah. So that was the merging case. That the scenario is, we talked about two, right? One is vehicles flying freely in the airspace, how to avoid collision. We talked about that. The second is merging, meaning that you are one vehicle is trying to change the lane, or a vehicle that is taking off has to merge into the highway. So we looked at those two cases. Third scenario, once again, it's a collision avoidance scenario. is something called a roundabout. This is another student, by the way, another undergrad student who designed this. Of course, he must have done a lot of literature survey to come up with the strategy, describing the geometry of the ride. So the beauty here is you're creating a circular intersection in the airspace. Obviously, it's similar to something on the ground. Nothing, not totally new, but taking this, the concept of circular intersection from the ground to the airspace and working out the geometry is the innovation. And this paper was, I told you, not only that it was presented in IEEE Vehicular Technology Conference 2024, and when he submitted a full journal version, he got reviews, and one of the reviews were very simple. One reviewer said, it's very pleasant to read the paper. In fact, so that's how we should be. You know, when you write a paper, you should put all your heart into that, you know, and make it the other person. Even as a professor, you know, when you read the paper, you should like say there is something to learn. Something, the innovation should come out, glaringly come out. Then people will like the paper. So and getting a paper accepted is not easy. So many papers. You know, one of the papers that I published. But again, most of the work is done by students. We only give the direction, idea. The paper went through 4 rounds. So it happens. It took almost like 3 years to publish a paper. But once it is published, it's become a very standard, very highly cited, one of the highly cited papers. So it takes time. But the more effort you put, the more what you call time you spend to read and reread, and try to present your idea and show the typically they will ask for look for what is new here. Is it what is new compared to the literature? In fact, my very first paper, when my PhD work, I did something called edge detection. When I sent the paper, they said the review was so what. So what means we're asking who cares for this. So you have to justify why this is why this is significant. What is the value? Here under the burden is on the author, not the reviewer, not the magazine. You have to show that this is important because of this. In fact, when we write funding proposal also is the same thing. My program manager say, its burden is on you to show that you're doing something new, and then you are capable of doing it, and then it is not done by other people and is going to make a change. So that burden is on us. The point is, this person, even though he's an undergrad student, he was able to write a paper that other people, reviewers felt that is he felt happy to read the paper. So anyway, this is the context. So here he come up with this kind of concepts, you know, action radius, action point, parallels radius. So read through this. The point which a US can enter and exit. So what are those? So here these are a vehicle is going towards north, enters the lane, and then it can exit from here, or it can go and exit from here, or it can go to. So basically identified those action points, A1, A2, A3, A4. Then he defined when do you start communication. So this term parallels radius is basically the radius of range of communication. First of all, that comes into the picture. So what he is saying is, when do you start communicating? In fact, I don't think I identified them here. But obviously this radius should be as a function of, it should be a function of the communication range. The radio should be able to communicate that long, that far. And these numbers, you know, I think these values or these variables will be clear when you look at the next. Yesterday I was looking at it, it didn't make sense in the slide, but if you go to the next slide, you'll see if you plot a graph like this, suppose r equal to 1, then you can see what exactly the meaning of r times square root 2 by 2. Square root of 2 by 2 is 1.414 by 2, which is 0.71. So these numbers come from those. Sorry. Yeah. So this, if suppose r equal to 1, then you can see this. Probably there are some minus signs that you may not be visible here. So for example, there is a minus here. You may not be able to see, but if you look at closely, you can figure it out. Okay. So basically, he designed the geometry. So ignore this for a second. Just focus on the how does a roundabout look like, and then what is the need for communication. So basically, once again, you are checking for the traffic. If there is a vehicle on your way, now remember the rule in circular intersection, the vehicle which is in the circle has a high priority. So you cannot just go and enter it. Before entering, you have to make sure that you have gap. It's the responsibility is on the vehicle that is entering. So, but the most important thing here is, the innovation here is how to create an artifact or a virtual roundabout in the airspace. And it is the fact that it is being reviewed, it was reviewed by peers. The peers accepted this. That itself is a sign. Your idea is not something totally out of like a wacky idea. Something. So and are they going to happen? Are you going to see roundabouts in future? May or may not. Hopefully we'll see the advanced air mobility is going to be very successful. If that is so, when that happens, you're going to see all. So all these things that I presented, all these are for now they are fictitious, meaning that air cell concept we talked about, lanes, corridors, all these things are you see here and there, but that's how research starts. And one thing is we are able to go so far, and maybe we can go further because it's brand new area, very rich. Okay, and then we were saying, and because vehicle to vehicle communication was started by us, in depth, not that other people don't have. Vehicle to vehicle communication is for the ground vehicles exists, but somehow it didn't take off right now. So we don't it has been more than 10 years that we had these radios for vehicle to vehicle communications on the ground, but also vehicle to infrastructure. Those standards were established, but we don't see them in action. That means we are not somehow things didn't go the way we expected. So, but the way things go forward is some research ideas turned into standards, and then standards being accepted by the community or industry, then only things will be successful. So everything that we plan may not work out. Same thing, what I'm pointing out here, all these research ideas may become a reality at one point, but it may take longer time. Yeah, that's a good point. You brought up a good point. Why are we doing all this? To enable automation in the airspace. And why autonomy? Because that's what we want to do, autonomous vehicles, right? So you're enabling autonomy, and as I mentioned, two things are important. Vehicles have to be autonomous, and you have to manage the airspace autonomously. Okay? And then the ultimate goal is, with minimal human intervention, you want to have the unmanned air transportation with minimal intervention. I think we can take a break now, right? Yeah. For us, we don't have need in the country. We have? We don't have need in the country. Whose responsibility is to yield? It is the red vehicle that has to yield because it's outside. So it has to reduce the speed. The ultimate, the result is, the outcome is that the red vehicle, even without negotiation, it will identify that it has to yield. So for example, you are getting the broadcast messages that both vehicles know about each other's location, and the position and location and velocity. The altitude and speed. Yeah, it's a good point. Actually, for now, even though we are dealing with the 3D space, we assume it is it's like a 2D plane, in the sense they are all the vehicles are at the same altitude. They're at the same altitude. Um, it's possible that probably we can consider other altitudes or multi levels, but we're not assuming. It's also possible to avoid collision. The two options. In generally. Well, for the probably electric vertical takeoff and landing, like helicopters. No, let's in this case we are assuming all of them. So okay. Yeah, obviously you're right. They cannot stop. Slow. You're saying if they are slowing down, can they maintain the altitude, right? For the quadcopters, yeah. But in general, it's But if it is a fixed wing, it's a different issue. But if it is like helicopter type of vehicles, they can maintain it. For example, they can even stay there hovering, right? Helicopters, yeah. Yeah. The other thing is we also, the other factor is we also assume that there is some space for flexibility to go up and down too. But but you're right. We are not going. Since it's only a simulation, we can assume that they're maintaining the altitude. But you're right. You have to think about same altitude. But in reality, you have to give some wiggle room for changing the altitude too. So ultimately this is what happened. So the red vehicle is yielding to let the blue vehicle go first and then go. Anyway, so this, by the way, the tool is called, it was used by the student, is called AirSim, and many people use it, and it's a very powerful tool. There are other options too. MATLAB, of course, you can do the simulations in MATLAB, and there is other tools called Q ground control. Many people who even you fly any small drone, you know that Q ground control is a tool that can be used for flying small drones as well. Another tool called PX4. In fact, Q ground control, literally Q ground control, that's the name, and then PX4, they go together. And what's interesting is these tools are used not only for simulations, but they are used for directly communicating with the drones also. So these tools are same tools you can actually communicate with the drones. So finally the drone could be a real drone or a simulated drone. Both of them work exactly the same way. So anyway, so we wrapped up this topic. So far we discussed the use cases and the message formats, the protocols like this. Like for example, we talked about right of way message, sending a right of way message, or requesting right of way and responding to right of way. With those two simple set of messages, you could implement a collision avoidance algorithm in the free space. And if it is merging scenario, you ask for request for gap formation if needed. In this case, it's possible that suppose the vehicles are continuously going, then you can request this vehicle to give a gap. So in that case, this vehicle will actually slow down. Suppose, say, I think just flip the scenario and say, in this case, the red vehicle allowed the blue vehicle to move first. But suppose red vehicle happened to be high priority vehicle, like an ambulance, then it's possible to request the blue vehicle to slow down, so and let the red vehicle go. That also is possible. But so basically, the gist is that the vehicle to vehicle communication enables this kind of negotiation. That's the key point that we are trying to do, right? So the third aspect that I wanted to cover today is a model for a vehicle to vehicle communication. Basically, it's a vehicle to vehicle communication framework not in terms, messages are done, use cases are done, but now look at implementation. So I didn't prepare slides for that, but I'm going to show you an article that is currently in preparation. We haven't completed it, but I'll show you some highlights or the idea of tunable model or a implementation of V2V. How do you implement V2V? And how do you choose the radio parameters? So let's take some time on this. So this is now our article in preparation. So basically the topic is the same. The topic is the same except that our focus is on implementation. So especially the radio. So how do you choose the radio parameters to implement? The rationale for this paper is that when I reached out to the program manager who was funding this project, vehicle-to-vehicle communication project, he said, Kamesh, I would like to see a tunable model. So what do you mean? What do you mean by tunable model? What is kind of tuning? So that's the point I'm trying to discuss. Okay, so look at the system modeling section. In fact, the first 4 sections are exactly what I covered here, and now we are focusing on the communication model. The focus still is on communications, and I think if in few minutes you will understand the big picture here. The first thing is start with the performance metrics. What are we looking for? We are looking for what kind of data rates that are possible. So in communication, data rate is important. Truly speaking, for this protocol implementation, you really don't need high data rate. So what are the messages you're talking about? Broadcast message, hardly few hundred bytes, and then we're also talking about right of way message or request for right of way, response for right. These are all at most probably few thousand, 1,000 bytes or 2,000 bytes. You don't need a lot of information, lot of data. And how frequently are you communicating? Probably the maximum is about 10 messages per second. So typically the minimum is 1 message per second or 1 hertz. In the critical scenario, probably you may be talking about 10 messages. Critical means the vehicles are so close, and then you need to avoid the collision. So in that case, during that time when you are actually implementing the negotiation process, you need to have more frequency. So but even then, 10 messages per second, 10 times 2,000 bytes, not a big deal. So you're not really looking for 5G kind of rates. That's not the issue. Okay. So but still you need to have an idea about what kind of data rates you can have. How do you find the data rate? That depends on what radios you're using, what frequency you're using, right? And then what's the bandwidth? And what is the path loss? Now you need to do all this. So that's exactly what we are discussing here. So let's start with the performance metrics. Data rate is one that we just talked about. Then range of communication, how far you can communicate. From the farthest distance the messages are expected to reach. So here is the crux or the crux. The program manager said, let's not fix the radio range. You give me a model where I will decide what should be my range. Is it I think the units are kilometers here, 2 kilometers or 4 kilometers or 10 kilometers. We will decide, because at this point there is no standard. Now how far you want to, what kind of radios you want to use, what frequency to use, how much the range, there are no standards yet. Okay. At most the closest thing that we have is by the way, it varies for different countries. The standards vary. Aviation standards are not the same for every country. So for example, the mandate of every drone has to have a remote ID capability. It's not universal. It's only in some countries. Okay. So given that, the need for why do you want to develop a model, tunable model? You want to change the range depending on requirements. But we know that communication range depends on how much is the transmit power, what is the path loss model, or what frequency you are using, and all that. So that's exactly what we are looking at. Third is you need to find a method of measuring or estimating the signal interference plus noise ratio. So signal to interference plus noise ratio. So SNR or SIN are also. So the reason we are looking at SINR is you expect interference. So what kind of interference? So when you really get into the detail, you will find, interestingly, the model simplifies significantly. And there are obviously every model has some assumptions. Try to grasp as much as you can. If you are a grad student, you already know some of the things, but if you're undergrad students, you may not know everything. But still, you get the goal is to make sure you grasp the idea, the concept first. So one of the key thing here is something called node density. Node density is required to understand how much interference you expect. So what is node density? How many vehicles are going to be present? So the one way to look at is, let's look at the worst case. Worst case is that the lane is filled with vehicles. So which means that since we are talking about lanes like this, so we assume that every cell is occupied. Okay. So we'll take a good example so that you really appreciate the idea here. It took several months, probably 2 years, roughly at least 1 year, to put on paper these ideas. But it's at the end of the day, it comes very simple. You will appreciate. So let's understand the idea of node density. So what is node density again? Node density is for a given unit volume, how many vehicles are there? That is generally called node density. That's what it's defined by the number of vehicles within a unit volume. So for simplicity's sake, since we are looking at corridors in the airspace, that's the beginning. So let's assume that this is consider this as an example of corridor. And if we have 1, 2, 3, 4, 5, 6, 7 cells, then there are 7. According to the rule, according to our guideline, our framework, we only can have at most 1 drone per cell. So that suddenly the problem gets simplified. You are not talking about 3-dimensional space, lots of vehicles. That's how we start actually. If you look at any other paper, and I will be happy to share this paper once, probably in a couple of weeks it will be done. I'll share that with you. But there are, I can give you certain references. There are at the end, but I will show that. You can also take a notes and then look for that paper. Typically, if you don't have any structure like this, the assumption is you have to think about what is the volume of the airspace and what is the density. Then you have to calculate how many vehicles are there. But in our model, there are restrictions. There is only, at most we have only 1 vehicle per cell. That oversimplifies the model actually, as you will see. So for example, he says, let V represent the volume of the unit air cell. So that's our unit air cell, and then it has dimensions of length, width, height, LWH. Now what is the node density then? Node density, because you are saying only 1 vehicle in the given volume, node density is number of vehicles over volume. As simple as that, right? So basically lambda is this. And then now you see how many vehicles are there. So you need to consider number of vehicles within the communication range. So where is the interference coming from? So look at the fine details here. Where is the interference coming from? If there are n number of vehicles, and let's assume the one vehicle is talking to the second. But at the same time, the first vehicle has a communication range probably up to n times the length of the cell. So it depends on the communication range. So interference is coming from all vehicles that are within the communication range. I think you should be able to see the point. Okay. If you are not able to, if the vehicle is not in your communication range, then you won't hear. And again, we are assuming that every vehicle has the same communication range. We are not looking at heterogeneous scenario. We are assuming that every vehicle has a communication range of R. So interference is coming from within that range. If there are n number of vehicles within the range, you get interference from n vehicles. So that is the idea. So we are saying how many vehicles are there within the communication range? If the L is the length of the cell, it's all suddenly it becomes one dimensional. Okay. So what I was saying is initially 3D is airspace is 3D, but now we are saying because of our conditions, we are the scope or framework that we defined, that you are dividing into air cells, and each air cell can have only one drone. Suddenly the 3-dimensional problem became a 1-dimensional problem. So how many vehicles are there? The communication range divided by the length of one unit air cell. It's always good to take an example. Suppose L equal to 200, then you can do all these calculations. I hope you see the point. Number of vehicles or number of air cells, both are same. In our case, number of air cells and number of vehicles are the same. Remember, we are assuming it's the worst case scenario where every cell is occupied. So it makes sense to say number of vehicles equal to number of air cells. Not a big deal, right? But how many vehicles you have to deal with when you are computing estimating the interference? That is given by range divided by length. So with that setup is so So you mean to say the signal energy, signal reception? Well, actually, really speaking, when you can't, I mean, normally, yeah, you're talking about transmit power versus received power, is it? Yeah. Yeah. But the interference we are looking at the reception. Well, actually, that I haven't even reviewed that. This is still developing. I'm not. Yeah, no, actually, ignore that part. Because this is some other the student has developed something. No, actually, let's ignore one and complete that part. I'm not. Let's completely ignore, because the point is it is still. I didn't even look at it. That is, the student has done something. I focused only on this part. So this where, yeah. No. The intention is to have an idea of what is the interference. Okay, right. Right. Yeah. No. Yeah. So what basically another way to look at is, let's say you have this is our corridor. Okay. So no, just basically you're looking at a snapshot. Let's say even though there are all these cells are there, our focus is only within the communication range R. So the question is, within the range, how many drones are present? And I think it's always better to take the worst case scenario, right? So because when you estimate, the ultimate goal is to actually predict or compute or estimate what is the maximum data rate you can get. So for that point of view, I'm considering that let's take the worst case scenario. That means at minimum that is the data rate you can gain. So basically I'm actually what I'm heading to is data rate using Steinern's capacity formula will compute the data rate. But before that, setting up the scenario. So in the scenario, even though there are a lot of cells, we're only focusing on how many drones are there within the communication range of one drone. That, right? So but you're right, but normally like basically even though there are a lot of vehicles, you're looking at a snapshot of at any given time, and then focusing within that range, within the communication range, and that's it. So, for example, as I said, my program manager asked me, give me a tunable model. If I want R to be 2 kilometers. So there are pros and cons. Now, one thing is you're only limiting the communication range to 2 kilometers. So what are the benefits? Your interference also will be limited. If your communication range is larger, you will have more drones in that, and that will lead to more interference. So if for example, if I want to say I want a 20 kilometer range, so that means you're able to communicate longer distance, but at the same time you also have to deal with all the vehicles within the 20 kilometer radius. So that's the point here. And to oversimplify, now what we did is, now how many cells are there in 2 kilometers? Suppose we're only looking at an example here. Suppose the cell length is 200 meters and your range is 2 kilometers. You have 10 cells, and because we are restricting only one vehicle in each cell, there are 10 UAS. So this becomes much simpler. Can you repeat? Yeah, is a constant. Yeah. So the density, node density is constant. That's right, a single occupant. Right, and also because we are looking at the worst case, we are saying that every cell is occupied. Because I think most of the times we always have to look at the worst case scenario. Yeah, it's not going to be there, but right, yeah. So practically, your results are going to be better, but studying the worst case is actually makes sense. And now we are getting into looking at the bond. Actually, yeah. Most of the time that's the right thing to do. Otherwise, you have to deal with some sort of a simulations. If there is only half the vehicles, half the cells are occupied, you can do those kind of things. Now next we come up with a way to estimate the interference. So try to look at this. Obviously, you need to come up with some setup. Transmit power is PRT, receiver power is PR, node density is lambda, transmit gain is GT, receiver gain GR. So we do all this, but at the same time, to simplify, we can set G gains are equal to 1. So basically, you're looking at isotropic antenna. See, everything is built from scratch, but notice, nobody can do everything from scratch. So you need to have some reference. So our reference is one of the papers that I found. I'll specifically show you. One paper that actually explained the things that we wanted. I hope this is still in preparation. That's why I'm asking you to ignore some of the things. There is one paper that I read that explained this interference concept very, very well. Yeah, I think it's not here. Yeah, there you go. This is the paper. 12 is the paper. It says interference analysis for coexistence of UAVs and civil aircraft based on ADS-B. This is a different setting, but this is the paper so well explained. If you are here, you may want to take a note. Notice this, write this paper, and it explains our work is based on these ideas, some of the ideas. So as I said, this research of course is incremental, especially when it comes to interference. And but other V2V is our own unique idea, but corridor concept. But in this case, in this paper, they considered 3D space, very general setting. We restricted that to air corridors. So that is our innovation, and model suddenly becomes so simple because of the assumptions that we are making. Okay. So I think let me show you the punchline first, and then we'll go back. Okay. I wanted to explain this as a researcher. If you are a researcher, this is the one example will tell you how we address the problem. The problem that was given to us develop a tunable model and tell me what happens if the range is, I want a radio that has 2-kilometer range or 20-kilometer range. Instead of fixing the range, we wanted to develop a tunable model, say how do things work when you put a radio with 2-kilometer range versus 20-kilometer. Okay, because we don't know what will be the standard. Okay. So what will be the expectations or requirements, they will come in future. So the best thing is to design something, a flexible model. Okay. So that is our intention. So with that, the punchline here is something like this. Yeah. So let's start from equation 14. We want the data rate. We want to estimate what data rates you can expect. Even though, remember, we're not really looking for high data rates, especially for command and control. But we know the Shannon's formula. We start from here. And notice this. I'll give you a little finer details because I'm expecting that somebody might be interested in B the bandwidth, and here gamma is the signal to interference ratio at the receiver. Remember, it's when we compute SINR, we are looking at the interference and signal interference and noise at the receiver. Okay. So I assumed, again, we can make these assumptions without losing generality. You can say my vehicle that is receiving is U1. I'm setting that vehicle 1 is my receiver. That means vehicle 1 is talking to some other vehicle. You can also choose transmitter and receiver, it's fine. So for example, our transmitter could be the last vehicle, receiver is the first vehicle. So that is the setting I used. You can change, you can make the changes, but still you get reasonably the same answer. And going back, we need to measure the noise. All right, and then you need to have a way to figure out interference. And the definition of gamma here, the gamma that we are referring to, is this. So follow this. I think if you understand this, you basically get the whole picture. We're saying the interference at vehicle U1, why U1? That's my receiver, is power of the transmitter, the product of gains GT and GR. I'll go through this once again, but this is the gain, and H is the fading parameter. We will go through that again later. PL stands for path loss, P is the noise, I is the interference. So basically, gamma is the power, signal power, that means the desired signal power versus are divided by interference plus noise. So that's this is standard, but now of course formulas are there everywhere in the textbooks and other papers, but you need to relate to your context. So you will see how they are related. So once you are able to estimate all this, it will give you the maximum data rate you can expect. Capacity is nothing but the maximum data rate. So this is our goal, and look at this, and this table tells you something interesting. Of course, you need to estimate, you need to compute all these parameters, and what is the end result? For those if you are only looking at high level, this is the big picture. If you want the range to be 2 kilometers, then the path loss is going to be 112.45 dB. Okay, in fact, I still need to review the paper. This is still work in progress. Okay, but I focused mostly on this model because the student is not familiar. He's an undergrad student. He just got into graduate degree program, but he hasn't done. If you haven't taken an advanced course yet. So for those who are in undergrad degree, unless you take an advanced wireless communication course, you may not be knowing all this. Okay? But what is that we are trying to do? I want you to appreciate that part. If you want to set your communication range to be 2 kilometers, then in ideal case, by the way, this is still in ideal environment, the transmit power has to be at least 0.175 watts. Okay, don't take these numbers as it is, but my point is, if you want the communication to be 20 kilometers, If you want the range to be 20 kilometers, transmit power has to be 17.53 watt. So look at this. Those are the numbers we want to get. We want to figure out if, depending on the communication range, how much transmit power you need to have. And it's practical also. Remember, I think in one of the some of the real world experiments, we use the mesh radio. With 1 watt, we were able to go probably 1 kilometer or something. But with we wanted 10 kilometer range, 10 mile range actually. To do that, we had to change the transmit power to 10. We didn't even look at the regulations and all those things. Probably we're not allowed to randomly change your power to 10 watt. But while we were doing the experiment, it's only one shot for about 20-30 minutes. We were able to do that. So my main point is, you need to compute all this, and this is not a rocket science. These path loss models are already there. But the interference, the main contribution here is how to estimate the interference. Okay, understanding where the interference is coming from, and then do those necessary calculations. So for the sake of I will go into detail so that you can see how the model is built. Okay, let's start here. Okay, so these are the parameters. Frequency refers to carrier frequency, right? Now we know that carrier frequency is important. Also bandwidth. Bandwidth is required because when you compute the data rate, you need to know the bandwidth. So anyway, so these are the system parameters. So this is, by the way, if you're working on any project, you are writing a paper, you have to first define all the parameters that you are dealing with. Then what about there is a path loss. Path loss also is very well defined, where it depends on the frequency and on the distance. Right? So path loss depends on the distance and frequency. So if you write in this, if you turn it into decibels, this is the path loss in not in decibels, but you can convert into decibel dBs. Then this is the equation. Again, I won't focus on too much on this because we all know that. Okay? And these numbers are obviously using the free space. To be more specific, this free space path loss. Okay? So we are not considering urban environment or rural. We are not even considering what you call difficult environments. Just simple free space path loss. And if you, one thing that I did is the first time when my student was presenting these numbers didn't seem to be correct. So what you can always compare, because these models are there in the textbook. You don't need to, you have some reference. So whether you have to check whether your reference numbers are meaningful or not by comparing. All right. Now the most interesting part is this part. So let's start from here. So far we only looked at the path loss, but our goal is to estimate the interference. So we considered a volume of airspace. We use a different variable, small l, small h, small w, to talk about the volume of airspace that are in consideration. And what does it depend on? What is the volume that you have to look into? That depends on your communication range. You remember, one cell has the dimensions of capital L, capital W, capital H. But the volumes of airspace where the interference is coming from, that has the dimensions of small l, small h, and small w. So follow this flow. I want you to really appreciate how the research problem is defined, how we are able to come up with a process of or procedure or framework for measuring what you are looking for. So we are looking at a scenario where a pair of drones are communicating. So here is the main idea. U1 is talking to UN. So you might be wondering, how can you fix it? You cannot practically you cannot fix it because you want to studying a general problem. But you can, if you think carefully. Okay, you are fixing the transmitter and receiver. You may pick anyone if you want, but the idea is to come up with as general solution as possible. This works actually. What we write in general paper in when you are writing a research paper, without losing generality, you are fixing the transmitter and receiver. So U1 is our transmitter, UN is the receiver. Sorry, it's the other way. U1 is the receiver, UN is the transmitter. Okay, and then yeah, we are setting the U1 is located in the first air cell, and the transmitter is UN is located in the last air cell. Okay. Then suppose say at the end of the, once you finish this, you are not happy with the model, you can make changes. But the point is you have to make sure that whatever model you are developing is general enough. Anyway, let me move a little bit faster. So the point, when one is transmitting to, sorry, n is transmitting to 1, how many vehicles are there in between? N minus 2. So where is interference coming from? From those n minus 2 vehicles. So you are saying first one is interested in listening to the last one. So there is a legitimate, that's a legitimate signal. U1 is getting a legitimate signal from UN, but all others may be talking. And what they are talking, who are they are talking to? Think about this. All of them. So while U1 is talking to U2, the other vehicles are talking to among themselves, or maybe they are talking to a ground control station. So whatever. Basically, every radio is active, and all the radios except the one and first and last are causing interference to the communication that is going on between the pair. Okay, see, and hopefully you can see, you can make sense. Okay, so what we are looking for is an average distance. See, in the previous case, we need a D, right? So how do you, what is the D? You're talking about a n number of radios here. So you pick, you are computing the average distance. So what is the average distance? Interestingly, it becomes like a sequence. So what D, by the way, what is the distance from where to where? You are looking at distance between any vehicle to the first vehicle, because remember you are estimating the noise and interference at the receiver. Which is the receiver? Is the first radio, which is in the first cell. So you need to compute distance from every cell or every drone to vehicle 1. Yeah, I hope you see my point. Okay, if not, without getting into making it too complex, that's what we need to compute. So basically, you are looking for what's the distance between cell number 2 to 1. It's one cell. What's the distance between third cell to first cell? Number 2. It's 2 cells. From 4th to 1, it is 3. So it's like it becomes like you're computing the average, right? So first you need to do the summation of 2 plus 3 plus 4 plus up to n minus 2. It's like a arithmetic progression, and that's where this number is coming from. So what is this? L is the distance between cells, and nu is the total number of UAVs, and the maximum is nu minus 1. Okay. So it's basically you are doing the summation of 2 to n minus 1. Okay, and that is this number. So once you compute the average D, that D you are actually substituting in this, in the path. So the notation here is PT is the transmit power, GU is a product of GT and GR, and we are assuming safely it is 1. So it's not really, but even though the values are 1, you have to give a generic formula. Then PL is a path loss, and what kind of D? What D you are substituting? You are substituting this D. So that is how you are addressing. You're creating an analytical model, and this model is not that we designed from scratch, but as I said, there is a reference paper from there. Okay, so that's how you validate. Sometimes you don't know when you can come up with a formula. In fact, that's what happened when I did my PhD. I published it and everything is fine. I still have a doubt. I had a doubt for a few years. Was this formula? Because I wrote the formula. I wanted to make sure it is. Is it valid? What happened was, yeah, over the time, I spent a lot of time. Of course, I talked to my mentor, my advisor, and I designed these formulas. But you always had the doubt: is it really valid all the time? But something interesting happened. Once my PhD was over, after 10 years, somebody else worked on the same problem. In fact, they said, your problem can be simplified if you do it in a Fourier domain. So that is a very nice, in fact, if somebody referred to the paper and then tried to solve the problem in frequency domain, that means that they really took time to understand the, suppose I write this, I publish this. How many people do you think will read? And how many people actually take time to understand, right? So, but if somebody has done this, that means that it has a value, it served the purpose. And again, we're trying to first of all simplify the model. Second is to achieve the purpose. The goal is to come up with a tunable. Anyway, something. Just take a minute. It allowed me to maybe drink some water. So this since yesterday, we were only focusing on drone-to-drone communication. We talked about use cases. Instead, we are giving a tunable model. So that is the big picture. And with this, we actually can wrap up this topic. There is actually today we are supposed to cover something called swarms, UAV swarms, but I will cover that later. And that topic actually, that work again was not only that we spent a lot of time, and the work was done. Work was a part of a PhD. It's a PhD work. The student who graduated spent about 3 years on this problem, on this swarming problem, and the results are what I'm going to present to you sometime later. So in about 5 minutes, we'll wrap up for today. So I hope this paper is still not yet completed, but once it's completed, and if anybody is interested, I will share that with you. I think. So we have path loss estimation here, and somewhere you should see the meaning of H, but basically it's like a channel gain. Okay. Yeah, so you can see the meaning of. So here the channel again it follows, we assume some distribution. So you cannot give any value for this. So this is where you need to do some Monte Carlo simulation to estimate interference and get some numbers, or when you want to plot something, you have to do some simulations. So at the end of the day, here is this model allows us to figure out what is the data rate that you can achieve. Given the, basically we're using Shannon's formula here. The only thing that we did here is all this work is to compute the interference. And these numbers will give an idea about how to choose the transmit power. If there is a flexibility, and if you want to go 20,000 meters, then you have to choose the larger power. And finally, tuning is possible. Okay, so that's the idea. The message here is you have a tunable model that allows you to design the radio based on any specific requirements. So let's stop here. We'll catch up tomorrow. Okay, in the afternoon, Dr. Sai Prakash, he is going to work on the lab. Thank you. Any questions, by the way? I said you can always ask questions in the middle, but do you have any questions generally from since yesterday to today, when I covered the idea of drone-to-drone communications, why it is important, and what is going on in the industry, and what is going on in the research world, and then use cases and standards. Okay, that's what I covered. To reduce what? No, I didn't get you. What? Oh yeah, sure. Oh, which one are you suggest? Oh, okay. No, actually, this case is more like we are assuming that there is a radio on each drone, right? So it is like something like a mesh network. That's right. That's what we had discussed. Because so our goal is to say, if you build a radio, and what should be the parameter? How far you want to, how much range you want to expect? But we didn't answer that question. We're not asking. So we're just saying, if you tell me the frequency, if you tell me the bandwidth, then we can tell you how far you can communicate, right? That's it. But the content, we're not depending on cellular, neither cellular nor. We're just having each drone having its own radio and trying to communicate. But in terms of if you want to compare satellite versus cellular, at a bigger level, at higher level, obviously SATCOM is good. It has its own benefits because it's ubiquitous. Right? It doesn't matter where the drones are, you can always have a satellite communication. But if you are looking at GEO satellite, then we have the issue of latency. On paper, you can say, well, even GEO satellite can support meet the requirements of latency, but practically it's not. Right? It may not be enough. So what we are talking about is close encounters. So when two vehicles are too close and you have to avoid accident or collision, you need a real-time negotiation. So probably geo satellite communication may not fit. And I'm just saying there are better options. You know, so if you talk about LEO satellite, obviously the challenge is more complicated because the LEO satellites move. You only get like the stability of the link it depends on how fast you can hand over from one satellite to another satellite. That is, even though in practice or in theory it's possible to do all this in real time, it's not about round trip time. Round trip time with LEO satellites is very good. It's enough to meet the real time requirements, but can we have the reliability of the connection? So that depends on how quickly we can hand over without breaking the link. Right? That's an issue. So satellite communication has its own limits. But there are products, you can always have a what it calls a satellite communication board. Or sometimes they are not only satellite, but also you can also put a SIM and make it both. You can switch from satellite to cellular. So those things are there, but in terms of meeting the requirements, real-time requirements, it is still questionable. You cannot say it works 100%. You cannot count on that. In terms of cellular connectivity, you may not have cell towers everywhere. So that's the limitation. So in some sense, the best way is to have all three. Both have satellite communication and have cellular communication as well as radios.
Resolution of satellite also important fact, like 10 meter, 20 meter.
You mean to say, yeah, the
Also is important.
right, yeah.
Drone to drone, 10 meter.
Sure, that's true. Yeah, right. There are, in fact, along the line, there are other issues also. What happens is, so we are saying
when a drone sends a message to other drone, we're assuming that by the time you receive the message and process the message, you're still thinking the drone is exactly the same location, but there are some uncertainty you have to consider. So suppose the location is X, that's X1, by the time you receive the message and process, maybe it's X1 plus delta, or minus delta. The delta depends on what is the maximum speed and all that. So that you have to give room for uncertainty. Yeah. Yeah. There will be difference. There will be. So we need to consider that kind of uncertainty into.
Your model you assumed the same speed.
Yeah, fine. Yeah, these are like since we are the early stage research, right? So we didn't consider the uncertainty. Right.
Uniform.
Yeah. So with all this, and in fact, uncertainty is not even considered here. So there is a lot of room. Usually the first person has an advantage that you don't have to do all this. But the next person is going to have to add something. Right. Yeah. Just the first model. You're right. But the interesting thing is not brand new because in a different context they have done. There are models. We only what you call converted that into corridor model. I think that's right. That's it. Yeah. The node density. The definition of node density is the unit volume. How many drones are there in a unit volume? Can you repeat?
Every unit cell, we are explaining this, and at one each channel and so on.
Yeah, no, every cell has the same volume, okay, but the dimensions are, we assume the dimensions of L, W, and H, right? So like a rectangular prism. Planar plane, they're in the same plane. Yeah, okay.
Taking unit volume only one extent. You cannot put more than one.
Yeah, we cannot have more than one. Yeah. Density you mean? Okay, no, but density is like, see, normally, first of all, you begin with the general definition of density, and then we are applying to our scenario, right? So, for example, when I consider the volume, what volume are we are considering? What is the volume of airspace within the communication range? So, yeah, like that's where multiple cells are involved. So R is the communication range. So within that range, how many cells are there, and how many drones are there? Because why do you need how many drones are there? Because the interference depends on how many drones are there. Like the interference is coming from other drones talking. Yeah, I think it does make sense. Yeah. 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 No, we can. The thing is, let's assume all the drones are talking. Okay, to somebody. Like for example, you and I are talking. Let's say other people are talking. Okay, so I'm interested in what you are talking, right? So I'm the receiver, you are the transmitter. But because there is no restriction in this case, because everybody is not talking because they hear you, and then they're respecting this conversation. But outside, that's not the case. When you are talking to me, other people will talk, right? So that's the reason you need to figure out how many transmitters are there. And we're assuming that every drone has a transmitter, and every drone is talking. Every drone is using the transmitter. So basically, there are n vehicles, 2 vehicles are talking, n minus 2 vehicles are causing disturbance. It's very simplified, very simple model. Yeah, I'll share that with you. We'll share that with you.
Same frequency.
Yeah, there's one more, exactly, one more thing is, we are not assuming that there is a what you call allocation, there is no scheduling, nothing. No multiple access, no scheduling, for which every person who is talking is actually a disturbance, it's causing. So, but if you have a schedule algorithm, yeah, just like this, when only one person is, when two people are talking, other people are not talking, basically we are scheduling somehow. But yeah.
Communication.
Mm-hmm.
Urban police, they use same frequency.
Right, yeah.
So many like
Right, everybody is talking, yes.
they can all hear.
Right,
But power is restricted, so
right,
this will not go to that side.
right, yeah, that's true. Yeah. So there is no sophisticated algorithms or anything, it's just a simple,
They are only watching.
right, yeah.
It's just 0.50.
Right.
It is the-
Yeah. Yeah. At the end of the day, I hope you have you enjoyed the session. And there's some simple problems, and I try to give a big picture and also give you fine research problem like this. Okay, well, that's my goal. Sure, wonderful.
Hello.
Okay, okay. కొంచెం volume ఇచ్చు.
Hello. Hello.
Good, sir.
Hello. Okay, we just start with the lab session, and I hope everybody is ready with the system. But don't worry, we are not going to start right now. Let me explain what we are going to do today, so that you can start working on it. So today we is the hardware and software lab, but we are trying to concentrate more on software lab. And if you can complete this exercise, then we can move to the hardware lab, right? So here we are going to study 4 different signals. When we transmit a message, the message travels by means of a signal. So the signal can be represented either in a BPSK or QPSK or QAM or OFDM. Right, the modern signals all we are trying to look into OFDM mostly, but earlier we have to start with BPSK 2 level phase shift keying, 4 level QPSK quad, and we are not looking for the primary QAM signal. We are going for a M array QAM signal where M is 16. As we are trying to look into the theory, we have seen that as M increases, the spectral efficiency increases. So 16 is we will be doing in the lab, and you can try also with 32 and 64 also, right? So these are the 4 modulation schemes we are trying to see. We transmit the signal, and then we try to decode it back and see whether the transmitted signal and the decoded signal are same or not, right? And we try to pass the signal through 4 different channels. One is AWGN channel, the second one is Rayleigh channel, fourth one is Rayleigh channel, and third one is Rayleigh, and fourth one is Nakagami channel. Okay, so if you try to look from the wireless communication point of view, mostly we try to use the last 3, not the AWGN. The AWGN will help us in understanding the system, and once we know it, we move on to a line of sight and non-line of sight and use fading channels. And the Nakagami gives you more closer by playing with the value of M. You can either move towards Rayleigh or move towards Rayleigh channel, depending on the environment. So if you try to look from the AWG channel, it is mostly, you can see that the signal is affected by all the frequencies. It's not by one particular frequency. Most of the cases, what we try to see is, if the frequency is narrowed down, some noises will be affecting, the other frequencies will not be affected. So that's how we move from frequency hopping, where there is no less noise, we move to that frequency and try to work. Instead of that, we should know where exactly it is affecting. So the pattern, what we are trying to look from AWGN will not give you any idea about the channel. We are taking a flat channel, having the noise effect similar for all the frequencies, and it is only for knowing that how the channel has to be modeled we try to look at. Then we try to move on to the relic fading channel, and you can see that most of the wireless today's system, they are not line of sight. We call it a non-line of sight, like mobile phone. You don't go directly opposite to the base station and talk, right? So as we move on from the fading channels, we move to the relic channel, which gives you more towards the no line of sight. We call it an NLOS, and we can see that the signal comes from reflected path or refracted path or diffracted or scattered paths and then receive the receiver. So in that case, we use this one, and you can see that interference has multiple components, and we can handle the channel mostly using really distribution, and this will help us to understand how the interference or the fading is affecting the signal. Then we have ration channel. It is dominated by LOS, and you can see that there is a parameter called K, which will help you to understand much better. If K, there is a K value which is equal to 1 and greater than 1. You are supposed to look into that factor. Play with the K and see how the channel is being affected with it. Okay? And mostly you can see that this is a very good model for satellite communication because you have a direct signal from satellite to ground station. There is no path between or obstacle between them, right? So you can see that most of the satellite communications, their model is using the Asian. Whereas mobile networks comes under the railing, and you can also see that if you have a small urban micro or picocell means you have a access point and your laptop, right? This is direct line of sight. It is not line of sight. You are not getting signal from reflected. Dominant is LOX. So when you are trying to look at a small micro cells or picocells and all, it is mostly dominated by LOX. So you can see that the satellites and the micro cells and all, they come under ration fading channels. If it is like obstacles like urban areas and all, it is predominantly we go for railing channels. And we have a very good one called as Megagami channel. It's a practical mode where both can be realized. Right? It is not that it is railing a ration. There is a factor called M. It tells you whether you have to move towards railing a ration. So it gives you a better understanding. If you are moving towards the channel, something like rural areas or urban areas or semi-urban or dense urban, you can play with them and reach to that point. Right? So you can see that dense urban environments are multiple strong multipaths are coming in now. Nakagami channels are much better. And you can adjust the channel such a way that you can cover all the regions. Rural areas you can cover, towns you can cover, urban areas, dense urban areas, satellite networks, all these type of satellite townships and all you can cover with. Even if you have inside your house, there are number of reflectors, like Almara is a reflector for it. Right? There is a table, steel table, it is a reflector for it. So in those models also, this will help you a lot. Right? So with these 4 channels and the 4 models, we try to do the MATLAB coding for that. So before we go, I'll just simply explain a simple code, and then you can start working on it. So let us take the first code, what is called as VPSK code, modulation and demodulation for AW Gian channel. So if you try to look at the first 3 lines, what we are trying to do is we are trying to clear the contents what are there in the memory, cache memory at that point. You write CLC, clear all, click close all. Means whatever is open previously, you are trying to close everything and making the screen ready for your program. Okay? So whether you like it or not, you have to add those 3 lines. Right? So make it a habit like whenever you open a MATLAB code, you just put those 3 lines. Otherwise, the last executed program can affect the present program. Right? So then you have n is equal to 15. The n is number of repeating the cycle up to 50 points. Like you are taking 50 input points and you are trying it. So that n we generate it from the data. You can see you are generating a random data of zeros and one, 50 numbers. Right? You are generating zeros and one, 50 numbers you are generating. That is what n is. Right? Random data we generally write 0 and 1. You want n 50 numbers of such data. And that is the binary data what you are taking. The external value is 20 dB actually. Okay, so you can vary the dB also, 40, 50, 60, you can do it, and also you can increase it or decrease it. Okay, so there is a built-in routine for you, which says that there is a BPSK tool which is available, which you can use it directly, right? Hello, sir, good afternoon, 5 minutes and I am coming down. Right, sure. So that is what we are using. There is a built-in routines like BPSK or the QPSK, QAM, and all are built-in routines. Toolbox are there. You are just using that command and calling that routine and using it, right? So that what you are doing, you are taking 2 into data minus 1. So your data is 0 and 1. So you are multiplying 0 with 2. So it is 0 and minus 1. So the resultant is minus 1. For 0, you are representing by minus 1. And if it is 1, you are representing by 1. So you are using minus and 1 for 0 and 1. It is 2 left. That's what BPSK is. Right? So you are taking 2 into data. Data is 0 or 1. And minus 1. So you are representing the data is 0. So you are plotting that and seeing what it is. And these are the titles you are giving it for the plot. Actually, I don't have it. I think the manual, if you try to look at it, you will get it. I think that will be circulated to you. The data will be for 0, you are giving minus 1, 1, you are giving 1. And this is the x-axis and y-axis, what you are filling up. X label is time, y label is amplitude, and title of the graph is input data. So this is what we are trying to fill it up. Right? This is only for plotting the data, how it looks like. And then you can see that the figure is complete. And there is another figure which you are trying to plot, BPSK modulated data. Earlier you are taking zeros and 1. And you are now representing BPSK modulated data minus 1 and 1. Right? So next, you are trying to transmit the signal through a AWN channel. AWN is a function already built in. You are calling that and passing the signal through it. Right? And you are plotting that again with the labels. Right? And then you can demodulate it and then plot it and see the data. So the MATLAB has a built-in codes, everything. We are trying to call the functions, using it for our signal, and plotting it and seeing what is at every stage of it. Right? So it should not be that difficult for writing a MATLAB. You are starting writing a MATLAB code. It should not be that difficult because they are all standard instructions for us. We are only trying to use that function. And these are plotting routines. This for every graph, you need a x-axis, y-axis, title, and what are the points you are representing. That's all we are trying. And you can put on a grid so that you can see on the grid where are the points. If you don't put this, the grid will not be on a plain sheet you can see. Right? So just spend some time, understand the code, and then try to run all these codes and see how it is. Okay? And if you have any problem, there is Harika, right? Harika and Paul are there. They will help you out in running the codes and see that the program is executed properly. Okay? You can start working on it. You will be here.